This is section 4.1, the inverse trigonometric functions. So let's look at this slide. First, let's consider the graph of y equals sine of x, and I'm only going to look at a chunk of the graph y equals sine of x, from negative pi over 2 to positive pi over 2, and look at this range that I'm considering as well. And what I'm going to do is I'm going to generate the graph of inverse sine. And this is what you get once you apply something that you learn in Algebra 1, Algebra 2, which is basically take the graph of sine of x and reflect it about the line here that is called y equals x. And once you do that, this is the graph of inverse sine. And notice that the domain is equal to the range in your inverse sine. And notice that the range for the regular sine is equal to the domain in inverse sine. And this has to do with, again, something you learn in Algebra 1, Algebra 2. The way that you find the x, the inverse is by switching the x and the y. So the domain values, which are your x values, now became your y values, and then your y values now became your x values. So here it is. This is actually the graph of inverse sine from here to here, just this much. Now, why do we only consider this much for the graph of inverse sine? The reason for that is because we want it to behave like a function. And we have to make those restrictions if we want this to behave like a function. So the restrictions are that on the domain is from -1 to 1, and the range is basically a consequence of the domain. So let me highlight the restrictions a little bit more. So here's the domain. So whenever you see this, the only x value that you can plug in has to be between -1 and 1, including the endpoints. And this is actually, we're going to make a special, we're going to place a special importance on the ratios that you saw on the unit circle. You're going to see other ones, but we're going to be highlighting the ones that you see in the unit circle. And then, so this is what the x represents. Now the y has to be, which is actually your range or your output value of the function. It's actually the angles on the unit circle, although we're going to be highlighting others that are not being highlighted in the unit circle. But they are going to be only angles that are between -pi over 2 to positive pi over 2, including the endpoints. Okay. So now, one last thing on this slide. I just want to make sure that you understand that sine inverse of x is not equal to 1 over sine of x. This is not an exponent that you can apply those rules of exponents that you learned in the previous math course. Let's go to the next slide. So now, inverse cosine function. Here it is. I'm just going to highlight this much because when I come up with the inverse, I want it to behave like a function, and it was agreed upon that we're going to only consider this much of the original, and then we do a reflection, and this is what we consider inverse cosine. And then notice the restrictions. The domain is -1 to 1. The range is a consequence of that. And just like on the previous slide, the x values that you're going to plug it into the inverse cosine function is going to be a ratio between -1 and 1. And again, these are we're going to place special importance on the ratios that come from the unit circle. And then the y values are going to represent angles from the unit circle. But here, the y values change from 0 to pi, including the endpoints. Let's go to the next slide. This is actually the graph of inverse tangent. So this is your original tangent of x, and inverse tangent is right here once you do the the reflection about the line y equals x, this is what you get. And notice that now the domain is actually all real numbers, and the range is actually now angles that are fall between negative pi over 2 to positive pi over 2. So now that we know inverse, sine, cosine, and tangent, and also their restrictions, let's apply that. But before we do that, this is what we highlighted. Now, there's also inverse cosecant, inverse secant, and inverse cotangent, and these are going to be the restrictions that we place on those inverse functions, and we'll highlight those when we get to actual problems that have to do with these functions. Let's go to the next slide. So here's number 1. It says find the exact value of each expression without using a calculator. So we have sine inverse of radical 3 over 2. And again, notice that this ratio is between negative 1 and 1, and is a ratio that you see in the unit circle. So just to make this a little bit more obvious, to bring the point home, read this. Basically what this is saying, this expression is asking you to find an angle, okay, given the restrictions for inverse sine. And if you remember on an earlier slide, the restrictions for inverse sine are from negative pi over 2 to positive pi over 2. So since this information is going to be mainly coming out of the unit circle, let's look at this picture. We're going to be considering just this portion of the unit circle. Notice that it's going from, this is positive pi over 2, and this is negative pi over 2. And notice that this is negative pi over 6, negative pi over 4, negative pi over 3. And you should recognize that these are the coordinate values for those radian measures. And these are negative coterminal angles. This is coterminal to 11 pi over 6, and you name it. Okay. So what we need to do is we need to find an angle that gives you radical 3 over 2. But we're looking at sine, so we're going to be looking at the y values of each of these ordered pairs. And understand, since the ratio is positive, we're not going to consider anything here. It has to be something in this region. And what is the y value that gives you radical 3 over 2? This one. So what is the answer? This angle. And again, the expression is asking you to find an angle, and given the restrictions that we have for inverse. And this is the angle. Let's go to number 2. So here's number 2. Before I continue with this problem, I just want you to get familiar with the notation. Arctangent of that ratio is the same thing as using this notation. Tangent inverse of negative 1 over radical 3. So again, what is this asking you to do? Read what it says here. Follow along. This expression is asking you to find an angle given the restrictions for inverse tangent. So if you remember the restriction from inverse tangent, I did not highlight this on the previous slide, is from negative pi over 2 to positive pi over 2. But unlike sine, here we cannot include the endpoints. We cannot use equal to negative pi over 2 nor equal to positive pi over 2. So once we look at the unit circle, this is what you consider. And since we're looking for an angle, and notice that the ratio is a negative, I'm not going to be looking at any angle from this quadrant. And it's going to be here, which you know is not going to be this one as well. This should give you negative 1. So it's either going to have to be negative pi over 6 or negative pi over 3. Out of these two, which gives you this ratio, negative 1 over radical 3. It turns out to be this one, negative pi over 6. So this is your answer to number 2. Let's go to the next slide. So here's number 3. Same directions as number 1 and 2. So what is this asking you to find? Again, this is asking for an angle, and these are going to be the restrictions that we have for cotangent inverse. And notice that the domain is any real number. Notice that this is a number that is more than, less than -1. And the range, so the only angles that we can give as an answer for any inverse cotangent has to be between 0 and pi. So we're going to be considering this portion of the unit circle from 0 to pi, not including the endpoints. So which gives you a real number of -3, and again is not going to be anything from this, technically what you will call the first quadrant. It's going to have to come from this second quadrant, and which one gives you -3 as the answer? It turns out to be 5 pi over 6. So this is the answer to number 3. Number 4 we'll do in class. Let's go to the next slide. So this slide is going to help you do the following. So whenever you want to find cosecant inverse of an x value, you can also just find inverse of 1 over that x value, given that it satisfies this. In the same manner, if you're looking for secant inverse of an x value, given that it satisfies this condition, just compute cosine inverse of 1 over x, and it gives you that same answer. And we have the same thing for if you want to find cotangent inverse of an x, you can use this expression that you have on the right hand side, or you can use this one. Out of these two, which one do I like better? Of course, this one. And then I'll clarify a little bit more what this slide is all about in class. Let's go to the next slide. So here it says find the approximate value of each expression without a calc. Round answers to 2 decimal places. So to do number 5, you need to make sure that your mode is in radians. And once you do that, punch in sine inverse of the number that you see there. And notice that this is a number that is between -1 and +1, which satisfies the conditions for inverse sine, and you end up with the following after you round to 2 decimal places. Number 6, same thing, cosine inverse falls within the restriction, this x value, and you end up with approximately 2.4. Number 7 is cotangent inverse. So what I'm going to do is, if you try to look for cotangent inverse on your calculator, you're not going to find that. So this is what I'm going to be using, something that you saw on the previous slide. Cotangent inverse of x is equal to pi over 2 minus tangent inverse of x. So all I'm going to do is I am going to go to change the color, excuse me, green. So instead of writing x here, I'm going to type in 4.32, and then do pi over 2 minus tangent inverse of 4.32. And if you do this correctly, this is what you should get on your calculator after you round to 2 decimal places. 0.23. Number 8, and again, you're not going to find this on your calculator, so you use this, which is on the previous slide, cosine inverse, and instead of writing, for the x, you're going to plug in -3.44, so you punch this into the calculator, cosine inverse of 1 over -3.44, and if you do it correctly, this is what you should be getting. Let's go to the next slide. So here says the directions are different. It says find the exact value of each composition without using a calculator or table. So this is a problem in which you have to do multiple steps. So first step that you're going to do is you're going to focus on this part of the problem and simplify that. It's asking for sine inverse of 1 over radical 2. and you should see that is equal to applying what you have learned in this video, and also by having a good idea of the unit circle, you should see that this is equal to pi over 4. So all this that you see here now becomes pi over 4. So you do secant of pi over 4, and secant of pi over 4 is equal to radical 2. So this is the answer to number 9. Again, one problem in which you have to do multiple steps. Number 10, same thing, multiple steps. So first you focus on this part, sine of pi over 2, and you know that from the unit circle is equal to, this is not, you don't have to consider inverse at all. This is just sine of pi over 2, which is equal to 1. So all this became 1. So now you have tangent inverse of 1. So you apply what you know about inverse tangent, and which angle gives you 1 for tangent inverse, and it turns out to be pi over 4. So this is the answer to number 10. Number 11, so we're going to focus on this part again. There it is. But before I do that, I'm going to use this here. So I'm going to be working with sine inverse of 1 over x, or sine inverse of negative 1/2. So which angle gives me negative 1/2 for sine? And it turns out to be negative pi over 6. And then I have sine of negative pi over 6. So I compute this, and you should see that by looking at the unit circle, this is just sine of negative pi over 6, not inverse. It's just regular sine of this angle, and you end up with negative 1/2. Let's look at number 12, and we'll do this one in class. So here's number 13. It says find an equivalent algebraic expression for each composition. Before I start working on 13, I just want to remind you of something that you saw in geometry, but also you saw at the beginning of this video, that inverse trigonometric functions actually represent angles or generate angles. So I am going to be looking at our cosine of x, which is the same thing as cosine inverse of x, and I'm going to let it equal an angle, which is going to be theta. Once I do that, I can rewrite this the following way. If you go to page 80, this was one of the definitions that you saw there. So this is equal to cosine of theta is equal to x. From here, I'm going to rewrite this right-hand side as a ratio, so it's going to be x over 1. And then from here, I should be able to draw a right triangle in which the adjacent side is x and the hypotenuse is 1. And that's what I have. Once I know this, I should be able to find this side here, applying the Pythagorean theorem, and it's equal to 1 minus x squared, and the square root of that. And then from here, I already said that this right here is equal to theta. So all I need to do is compute tangent of theta. Looking at this right triangle, tangent of theta is equal to radical 1 minus x squared over x. And this is the answer to number 13. The last one, number 14, very similar to 13. I'm going to let this, again, rewrite this as sine inverse of x, and this is an inverse sine, which means that I can let this equal to an angle. I'm going to let it equal to theta again. Same thing, definition of inverse sine, page 80. I can rewrite it the following way. Write it as a ratio. From here, I should be able to draw a right triangle given the reference angle theta, in which the opposite side is x and the hypotenuse is 1. I find this missing side using the Pythagorean theorem. This is what I get. So now that I have this, I should be able to find secant of, again, we let this equal to theta. So secant of theta, by definition, is equal to the hypotenuse over the adjacent, and this is the answer. And in this case, we don't have to rationalize. This is the answer to number 14.